we went back and refreshed on how do we determine relative ages, relative sequence of events using the fundamental principles of geology. We also talked a little bit about absolute dating, looked at the geologic time scale, looked at the time scale really as a living document, because this is something that is undergoing revision, review worldwide. There are international commissions that deal with making sure that we have an accurate document, making sure that we have the best sequences, the best system of rocks to define those boundaries and to define that time. And so this is something that is ongoing. The other thing that the International Commission is really involved in is trying to have truly a single document as a time scale that is used in each country. Because what happened prior to about really 20 years ago, each country had its own time scale where the major divisions were agreed upon, but the minor divisions, the ages, were not, because the rock systems are a little bit different and each country, and so we had more of a European time scale, more of an African time scale, a Middle Eastern time scale, a Far Eastern time scale, North American time scale, South American time scale, and it became confusing and difficult for geologists around the world to work together. And so the International Commission really got together and tried to figure out, can we standardize this? And there's still work to be done. In North America, we have several stage names that have not yet been fully flanged up into the current international timescale. And so if I say that I'm dealing with Demoinian rocks, that is a North American terminology for a stage name that is not yet fully matched up with the time scale. It overlaps partially with Muscovian, but not entirely with Muscovian. So there's still quite a lot of work that needs to be done in order to have the time scale serve as a truly universal document. Okay, now, one last thing we want to think about is, can we reason out one last puzzle? And I want to put up a slide. Here's the slide. This particular slide is in Wyoming. This is just outside of Laurel, Wyoming. The system of rocks that we're looking at is rather unique. You can see a highway coming down here. What we see in this particular outcrop is quite interesting. If we just would start making a few observations, what sorts of things do we notice? Which way are these rock layers dipping up here? Are they horizontal? Are they dipping back into the board? Are they dipping out toward us? Any thoughts? Yeah, they're dipping back. You can see this contact right here. So these rocks are dipping back into the board. Now, when you first look at that, you say, okay, this is a very nice succession of rocks. Looks quite normal. But when we start making some observations, we're going to come up with a few issues that we have to try to figure out. If we look out in here, see these lumps? It's kind of lumpy out here. This is a landslide deposit. This is what we call a repair cushion landslide that came off of this. So this face, this topographic face, is actually a landslide face. The landslide partially cuts right through here and a little bit right through there. So this particular road, this is Highway 14A, that goes from Douglas to Lowell what we're looking at, that particular road is always being repaved. Every single year they repave it again because it's an active landslide. We are actively slumping. This is actively slumping downward relative to this side and to that side. So the highway department, in its infinite wisdom, is doing exactly the wrong thing. They keep putting another layer of pavement on top of it, and so effectively they're jumping up and down on top of the active landslide, causing it to continue to creep down. They should know to actually try to stabilize the toe of it rather than continually to add things. And there are times of the year that you drive through here where there's as much as a 1 foot drop as you're driving along the highway. When we look at these rocks, you notice some reddish colors in here. You have in here some sort of tan colors. Last time we saw these two colors, one was the Permian goose egg, one was the Pennsylvanian tinsley. So when we start walking around up here, we're going to determine that this is Permian goose egg. Right there. This here is the tinsley, Pennsylvania. As we come up, this is the Devonian Madison here. And then on up toward the top of the hill, right at the top of the hill, that's Precambrian. So, are you okay with that? We have Permian, and on top of Permian we have Pennsylvanian. Then on top of the Pennsylvanian we have the Devonian, and then on top of the Devonian we have Precambrian. Are you okay with that? That is upside down. This system has been completely inverted, turned over. There is a thrust fault, and that thrust fault exposes quite beautifully. You can see a line running right through here, goes up there a little bit, comes down right through here. That line divides the goose egg and upper goose egg. This material is Cretaceous layer formation. So we have a break, we have a fault here where these materials have been turned over and thrust out toward us. So the way that the original geologists working in the area recognized that we had a problem was, number one, they were familiar with the formations that they were seeing throughout this particular region. There are some beautiful indicators of younging within the tin sleep, within the goose egg, beautiful cross beds within the tin sleep that are pointing the wrong direction. We're pointing towards up being this way in the photo. So unless I'm standing on my head when I took the picture, something is not right in this system. We can piece even some of these very complex stories together by using the very, very fundamental principles that we learn in physical geology, which turn out to be extraordinarily powerful for us in the field when we're doing mapping, even if we're dealing with a very complex system. So, as you go through, read through all of those materials. If you have not chosen a GSSP, if you have not chosen a time span to investigate, please indicate your choice on your card today so that I know what you're working on. Remember, homework 1 is due on Friday, and that is to build a complete table including several columns of information from the timescale program and to determine, find out one of the GSSPs that you're interested in and look at that paper, read that GSSP. You can download those from episodes and give me a summary of why that particular contact was chosen at that locality. Those localities are around the world. And so that is coming up due on Friday. So now what we want to do is we want to change gears a little bit. We want to move into fractures. And I think it would be useful, you can let me know otherwise, to run through some of the slides on fractures, begin looking at some of the geometry, some of the relationships that we see in fractured rocks, try to come up with some fundamental understanding of what fractures are, and most importantly, why should we bother? Why should we even bother with trying to understand fractures? So, let's get started. So we're going to look at this slide set. First set we're going to look at is what I call a regional fracture. And this is a fracture set or fracture sets, multiple, that might be found in a large region where you might have had a large scale uplift, where, let's say, you look at in the state of Utah, we had a very broad uplift giving us these large fractures that repeat, and they can form by one of multiple reasons. Here I use a term, mode 1, and we may want to think about what are the different modes of fracture. The easiest way to think about the modes of fracture, a mode 1 is a simple extension fracture. So I'm going to click one more light on and draw this on the board. A mode 1 fracture, basically we can envision having a material where these boundaries are actually infinite. This is a flaw in the material, and what we're going to do is we are going to pull the material exactly perpendicular to that fracture plane. And so that's a mode 1 type of a flaw. If I take this and instead of extending, if I try to apply a shear load on this, that would be a mode 2 flaw. And I might have one other geometry of loading. And in this case, what I'm going to do is I'm going to apply torsion. I'm going to try and tear it. And so this would be like trying to tear a phone. That would be, what's your guess? Mode 1, mode 2, yeah, mode 3. So this would be a mode 3 flaw. Most of these regional fracture sets are typically mode 1 types of flaws. Now, do you see any fractures here? We're down in the Wichita Mountains. What do you see? Anything? Other than rocks, blue sky, there's a tree. What are these? Those are large-scale fractures that extend for tens of kilometers. So these are a regional set of fractures that would have formed in this granite. The granite behaved as a relatively homogeneous material. Since these are vertical, we can see them over great distances, and they seem to correspond to uplift of this particular block. So this will be our regional fracture pattern. This particular area is Elk Mountain in the Wichita area. Do we see any fractures here? We've changed location. We're down on Eufaula Lake. If you go on the Sedimentary Rocks and Processes field trip, you'll go to this outcrop. But Dr. Kerr won't be pointing out the fractures. He'll be pointing out the sedimentary system. But since I'm a structural geologist, we have a beautiful set of fractures. What we see is you see fractures cutting through like this, and you should also see fractures cutting through like that. So we have what is termed a conjugate set of fractures, likely due to extension in the Arkoma Basin, which the Arkoma Basin will be to our right in that. So partially unloading and partially an extension of it, giving us these conjugates. These are classic conjugate fractures in that system. If we look in the next area, we've gone out to, we're near Salida, Colorado, along Highway 3, right along the Arkansas River. This is the Sangre de Cristo Formation. Here is Pennsylvanian age. The rocks were deposited during the Pennsylvanian uplifts that we see in the area. Do you see fractures? We have fractures, and you can see these faces here facing toward us. That is a fracture that's cutting back like this into the board. These faces are cutting back at an angle. And so the fracture sets that we have are almost vertical here and are giving us this face, step back, face, step back, face, step back type of a geometry. And so all of this is related to fracturing. This is a regional fracture set that is due to the later stage uplift of the Sangres, both in Laramide, but more recently in Eocene time. So this is a very nice set of fractures in this system. Are there any fractures here? Yes. Just a couple. When we look at this, this is the Greenhorn limestone. It is Cretaceous in age. It is this, we are near Grape Creek. We're in a field area called Grape Creek near Kansas City. We can see some incredible fracture density, very highly fractured. One thing that we tend to observe in rock material is that if we have a relatively simple deformation, and this is actually a simple deformation that occurred in this area, thin layers, and the Greenhorn is composed of a series of thin limestones with shale on either side. Thin layers tend to have more fractures than do thicker layers. Now, when we look at this, we can actually start to deconvolve how many unique fractures we have. And the exercise there is to see if we can take one of these fractures, let's take a look at this one. That one actually repeats on a very regular scale, on a very regular basis. And so that is one good fracture. This fracture repeats again and again and again and again and again and again in that system. And so when we start piecing this together, there's really only about 3 unique fractures in here. They've just been repeated several times over. So this is a very nice set of fractures in the Greenhorn Formation due to laramide again deformation. If we go up into the Dakota sandstone, where we were in the Greenhorn, now we've climbed about 1,500 feet. We're up into the Dakota Formation. This surface, see this surface here? That is striations due to a little bit of fault displacement. But we have these lines coming across. These are fracture sets. And we have some that are at a slightly different angle. In here, the intensity, the density of fractures is far less. But we've not gone that far, have we?
You said those striations were due to
Yeah, there was a fault that was displaced, and then this block on the fault has fallen off.
Okay.
So these are slicks, what we call slicks. So in this case, these fractures are much further apart than they were in the Greenhorn. The Dakota is a little bit more competent, the bedding is a little bit thicker. And so the same basic stresses, the same basic reasons for the fractures give different patterns depending on which type of formation you're in. Now we've jumped down to, where are we? This is, it looks like Zolto. Oh, Leatherby Quarry, okay. Do you see any fractures?
Yes.
So we have this fracture right there. You see that face here? There's another face over here. This is a fracture face here, so that we have at least 3 dominant fractures in this particular system, and there's one more that gives us this type of, this comes out at us over, steps back, and across. So different fracture spacings, different sorts of systems. This particular quarry, the fracturing is actually so intense that you can go up and with very little force you can just break the rock into almost gravel size pieces because it has been so intensely fractured in that particular system. Now, do we see any fractures here? We're up in the Black Hills, South Dakota. This is the Harney Peak granite. The Harney Peak granite is about 2.7 billion years old. Do we see any fractures? What's the orientation? Are they horizontal or are they vertical? Pretty much vertical. And they're allowing the Harney Peak to weather out in these sorts of pinnacles in this particular system. And those are characteristic of fractures within a relatively thick sill. This is a granitic sill in this particular case. Now, are there any fractures here? Yes. This is the Giant Springs at Great Falls, Montana. This is an artesian system. The reason that we're interested partially in fractures is because they allow fluid to flow. This water that you're looking at here was sourced really about 160 kilometers away. It flowed through the subsurface. It was sourced in the Beltian region, the Little Belt Mountain uplift, flowed through the subsurface to the exposure right here on the river. This flow rate is about 156 million gallons of water per day. Tremendous flow rate in this particular system. And so fractures help control fluid flow. If you are working in an aquifer, fractures become incredibly important because they're going to impact how the aquifer behaves. If you're looking at a system that has a contaminant, and the contaminant is flowing through the subsurface, The fractures are going to control where the contaminant is flowing. If you're looking for oil and gas, then you're going to be intrigued and you're going to want to know about the fractures because they would impact the behavior of your reservoir. If you were to drill a horizontal lateral in here, if you drilled a horizontal lateral straight along this way and missed the fractures, you would have very low porosity, very low permeability. If you drilled a lateral across this way, it would flow like gangbusters. So that the behavior of your reservoir, your aquifer, your contaminant flow is going to be impacted. Fractures form in any type of material. Here we have fractures forming in evaporite deposits. We're out at Alabaster Caverns and near the Panhandle. Now we've jumped out to Monument Valley. It's scenic, it's beautiful. Monument Valley is a fabulous place to visit. Do you see any fractures?
Yes.
The fractures are what are controlling the formation of the mittens. The East Mitten Butte, the West Mitten Butte are controlled by fractures. You have a vertical set of fractures, and you can see that it changes spacing in different layers. Different layers will reflect different spacings of those fractures. So here we have a classic example. Now, fractures that form in igneous materials. This is Pikes Peak. Here, does that look completely uniform, or does it look like it's fractured?
It's fractured.
It is unbelievably fractured. You have dominant fractures that are near vertical in there, an occasional horizontal fracture in the system. That is a massive granite that intruded about 1.1 billion years ago, and we're looking at fractures that developed tectonically. Now, this is Devil's Tower, Wyoming. Do you see anything? These are fractures here. This is something that we call columnar jointing, and you can see the end of one. It looks relatively small until when you start looking around on this, and you can see the people down here nearby, and there is a person just right there, a little speck. That's actually two people working on a rappel. So these columns are about 2 meters across. So these things are enormous. These are cooling fractures, where we had a stalk intrude and then cooled, we shrank a little bit, and we formed these columnar joints in that particular system. We have sheet fractures, slightly different view of Elk Mountain, different time of day. See these beautiful surfaces here? These are sheet unloading fractures. And the easiest way to explain a sheet unloading fracture is to imagine that we have a situation like this. Our first step, we intrude a very large granitic body at depth. It might be buried 5, 6, 7, 8 kilometers. So it crystallizes and solidifies under pressure because it has a confining pressure, and anywhere that confining pressure, basically we can express as rho GC. What is the depth? What is the density of the material? And gravity. So that's the confining pressure. Now, subsequently, if we have time And now we bring this to the surface. We've released that pressure. Granite, any other rock material, will expand slightly. Imagine, if you will, let's take a balloon, go down a few thousand meters, try to inflate the balloon. It's going to be tough. Get the balloon inflated, and then if you bring it to surface, what happens? It expands. Same thing happens here. And so we tend to form these large sheet fractures that mimic the topographic surface. Those are local in nature and are showing us what the geometry of that intrusive body looked like, and shows us the expansion of the material in the sheeting process. So here's some sheet fractures in the Wichita's. Now we're out in Rocky Mountain National Park. This is Chasm Falls along the old Fall River Road. And you can see a suite of fractures. All of them horizontal to subhorizontal. Those are sheet unloading fractures in the Long's Peak granite. And these are classic Mode 1 sheet type fractures in that system. And this is Gail, and she's about 5'2", so you can get a sense of scale of how far these are separated. We can also get exfoliations when you have a mass that gets completely surrounded by fractures. It starts to come apart like an onion peel, and you get exfoliative fractures in that particular system. Now, dikes also very often behave like fractures. And so now we're down in the Wichita Mountains. We are we're standing on a railroad track, Burlington Northern, and you want to be careful because it's used fairly frequently, and you can't hear the train coming. So it's wise not to stand on the tracks for too long. We have this granite coming across, and then it terminates right there. There's a flat termination for that, and then you have a little coming off here and a little bit coming off here as it was trying to propagate, but didn't have enough pressure to propagate out. This is propagating as a Mode 1 flaw, a Mode 1 fracture. Now we've jumped over, we are in the Cold Springs Quarry. This is an old quarry, and you have two dikes that are propagating. This one is propagating in this direction. This one is propagating in this direction. And you can see when their stress fields overlapped. And the two perceived each other. And it caused them to refract and then join up as they were propagating.
Can I ask you more about the 16 dikes and cross-country dikes? Are they the same?
The age, these were propagating at the same time. And so this is a late stage granitic intrusion in the area, and it was coming in along joints. Then once you get to a certain point, the stress fields begin to overlap, and that causes that to bend and join. So they're not cross-cutting each other, they're cross-cutting this, but they were propagating at effectively the same time. Right here, this fracture intersected this one's stress field. Right there, this fracture intersected that one's stress field. And so they refracted and joined. Does that make sense? Okay. So If we look, we can have fractures, fractures that are related to folds. We're back into the Bighorn Mountain area. This is a beautiful monocline. You can see the rock layers come out, bend, and go vertical right there. The dip of those layers right there is 85 degrees, nearly vertical. You're looking here, from here to here, you're looking at, we pasted out, I think it's close to 1,400 feet of relief. So this is relatively thick. This is the Madison limestone, looks like the Madison limestone here. And you'll notice some fractures in here. If we turn and look from the other direction, straight on, you can see fractures with this orientation, fractures with that orientation. We see some fractures that appear to be nearly horizontal, so that we have fractures associated with just the bending of these layers. Now again, keep in mind you're dealing with, now we're looking at about 1,800 feet of relief. And the Bighorn Medicine Wheel's up on top there. It's overseen by the Crow Nation. And we also have a very nice U-shaped valley coming out of here. So this was glaciated and helped us expose these beautiful fractures. If you go back in there, it's kind of treacherous, difficult climb. Now, here's a slightly different fold. This is Split Mountain Anticline. We're looking at one limb of the fold coming down. This particular fold you can see on satellites, and you can see fractures all the way across this thing. So these are fold-induced fractures, fractures that form due to folding. If we look on, this is off of Bing, I believe, Bing Maps. We were up here looking into this. The previous photo was this part of the anticline, and you can see the large anticline here. And I don't know if they put a scale on here. Yes. So this distance is about 1 kilometer. So this is about 1, 2, 3, 4 kilometers across. It's a relatively large feature. And if you zoom in, it's really nice to, on Bing, to zoom in and out, and you can really see the fractures associated with that folding event. Fractures are ubiquitous. We find fractures in all rock types under all different conditions. Now we've jumped out to the Grand Canyon. We've seen this slide before, I believe. You can see intense fracturing in the Kaibab. This is the Toro Weep up here. And that forms this sort of step back, step back, step back, step back, step back geometry of that exposure, entirely due to the fractures associated with the East Kaibab monocline in this particular area. We're jumping all over. We're now in, we are in Zeisman Dome, near Tin Sleep. Zeisman Dome is a large fold in the system that exposes several of the sequences of the Pennsylvanian Tin Sleep, Aeolian Berg. And we can see that we have not much fracturing, and then we pick up a zone where we have quite a bit of fracturing in the system, and then it drops off again. And so we tend to see swarms of fractures from time to time, where you'll have a bunch of fractures very close, then not much on either side. And we tend to call it a war zone. It fits if you look at the mathematical modeling of these, it fits a rather interesting statistical modeling called a war zone. These are features that form when fractures can infill with slightly ground up material. And we end up with these sort of fins sticking up. These are deformation bands. The poor student that I cut his head off, this is Scott Azar. If you're in petroleum engineering, you've probably heard stories about J.J. Azar, Dr. Azar, that's his son. But he wanted to go up, do geologic field mapping, and the computations he's working on, he's actually trying to do a flow model for that particular system. Looking at the permeabilities that we were able to measure. And so these deformation bands can enhance fractures. We see these beautiful fractures cutting through here and these sorts of deformation bands in this area. So fractures form in all rock types under almost all conditions that we can see. Boxwork structure, this is in the Ouachita Mountains, just outside of Hudgens. It's just outside of the, in fact, it's just across the fence from the correctional facility, so the guards get really interested when you're overlooking at this particular outcrop. They want you to count the number of people getting into your van and make sure none of them are wearing orange. So these are wonderful, wonderful box structures in the system. And then we can see small scale features. Here we have a tension gash, a fracture that opened up that is relatively ductile when that particular thing opened up. This is in the West Creek Formation in, where are we? Mill Creek. We're in Mill Creek, right next to a hunting cabin, actually. And now we're at Limestone Hills, and you can see these tension gashes, which are a type of ductile fracture. These are indicating shear in this particular case. And we will see features like this when we go on our field trip. We will see these sorts of tension gashes in that system. So fractures form in all rock types under an incredible range of conditions. This particular sample, this is a slab of a core. The core was taken from, I believe this was Safa Field in Iraq. And it was given to Dr. Presmentowski to help the engineers come up with a flow model. And he brought it to me to look at because he thought these features here, these are called stylolites, might be impacting flow in the system. And I pointed out that, you know, Dennis, you've got these stylolite-induced fractures in here that are going to severely impact your flow model. And so they changed the flow model because of that observation, because those stylolite-induced fractures had really modified the way that particular reservoir was behaving. So fractures form everywhere, all sorts of geometries. Now we're up in Nova Scotia. Here, this is the Goldenville Formation. You can see these beautiful little mud volcanoes, primary indicators, and then you have this zone of fracture, and those are pinnate fractures in that particular system. So fractures form in all the rock types. You have some intriguing things that happen when fractures propagate. Fractures are not infinite. They have an initiation point. They propagate, and a lot of times they propagate relatively quickly at near sonic velocities, and they leave behind these sort of features along the surface, this type of haggle along the surface so you can see what those fractures were doing at the time they formed. So, more twist hackles, and that leads to a global pattern. This particular pattern is a suite of dikes. This is east and west Spanish peaks. You have, these are both 14ers in Colorado, 14,000 foot peaks. So we're looking at very large scale here. This is about 5 miles. These dikes are propagating as mode 1 fractures. And this makes a very, very interesting story, because when you look at the dikes, you would expect them to be relatively straight and relatively uniform around the volcanic system. These are volcanoes here, but there's a difference. The dikes are very short on this side. They tend to curve and become much longer out here, sweeping out away from this system. And then they don't cut across the Sangre de Cristo block here. They cut across the Leveta syncline, but they don't cut across this. So what happened here apparently is that this block was acting as a rigid barrier, undeformable barrier, when these were propagated. And so they tried, but they could not cross that barrier, so you started deflecting. And most of the pressure was released out this way in the form of those dikes, in a weaker, slightly weaker material, where the dikes could form. And when you look at these dikes in the field, they may stand 10, 20 meters in height and extend for kilometers. They're extraordinarily large in that system. So what we're going to do, this is the satellite version of that, and we'll stop here. This is Shiprock here. This is Shiprock in New Mexico, near the town, oddly enough, of Shiprock. This is a single dike coming out of that. This is a basaltic dike coming out of that towards us. This site is has great significance to the Navajo, and there's usually a Navajo policeman that prevents people from driving back unless you stop and talk to them. And if you talk with them, they'll let you go up into Shiprock, which is quite a fabulous lookout. Okay, so fractures form in all different materials. Fractures can serve as conduits for flow. They can serve as barriers or baffles to flow. They can strongly impact the way an aquifer will behave, the way that a reservoir will behave. And so we'll go back on Wednesday. We'll start looking a little bit more, review the geometries of fractures and fracture systems. Your book does a rather terrible job on fractures. Haken does not like fractures, and so he just didn't put them in the book very much. So we'll have to build up some of our understanding of these fracture systems. All right, cards, and I will see you guys on Wednesday.
Headlights نفس الباكشة لايت كامل باكشة شو دائما توحك الصوت
لازم بسرعة لا بدك تكتب سؤال
ها؟
لازم تكتب سؤال لازم تكتب سؤال لا ما لازم يجوز ما عندك تكتب